Hello, everybody. In this video, we're going to be going over a quick sorting, a review of the 4 sorting algorithms that we have learned currently in order to better prepare you for your homework and this week's discussion worksheets. All right, so the first sort we're going to look at is selection sort. And the general method of selection sort is that we're going to first look through the array, the list, and we're going to find the smallest item in the list. We're going to swap this item with whatever item is at the beginning of the list, and we're going to fix this item so we can no longer swap it, right? Then we're going to repeat this value for unfixed items until all the items are fixed. And so how does that work? Let's look at this example list of 3, 8, 0, and 7. First, we're going to find the smallest item, which is 0. Then we're going to swap its item to the front, swap it with 3. As you can see, they're switch places, and we're going to fix 0. So now we no longer have to consider 0. Next, we're going to find the smallest value from 8, 3, and 7, which is 3. Then we're going to swap 3 with 8, and we're not considering 0 anymore because 0 is fixed, and we're going to fix 3 as well. Then consider 8 and 7. Well, we're going to swap 8 and 7 because 7 is smaller than 8. And then we are fixing 7, and finally there is no more values left. There is just 8. So what is the runtime of this function, right? Well, first of all, we can consider how long does it take for our function to find the smallest item? And the answer is it takes n time, right? Because you have to iterate through every value in the list, and that's going to take us n time. That makes sense, right? However, it is a bit complicated because our list is getting smaller over time, right? And so our runtime actually lists a little bit something like this, right? Where the first pass through is going to take n time. And remember, swapping is constant time, right? Because we're always swapping with the same value. So this is going to run in n time, and then because our list gets smaller, it's going to run at minus time, then ... until we have 1 time, right? And so our total runtime is going to be sum of all these values. And if you remember from our asymptotics review, this sum is actually going to come out to theta n squared runtime. And so selection sort is not very fast at all because it is a rather primitive sort. And so now we're going to look at some examples of sorts that are a bit more optimized in that regard. Heap sort. So heaps already access objects in sorted order. So a natural idea might just be to put all of our values into a heap in order to access them like that. So and then accessing items in a heap is going to be subject to all the classic things that we have to do with heap that surely you remember from our midterm review. So selecting the largest item in a heap is very fast. It is in theta 1 runtime. However, removing the largest item can take a bit longer because you have to sync our new value. So that's going to take O log n runtime. Sorting items into a heap is going to take O n log n. And the reason for this is because inserting items into a heap takes log n time, and you have to do that n times, right? You have to do that n times. And so our worst case runtime is O n log n. Now, there are 2 main ways to do heap sort. And the first one is called naive heap sort because it is naive. You should not do this. And essentially what it's doing is that we're just creating a new heap data structure that we're putting all of our values into, right? And so this takes the same amount of runtime as any other heap sort. However, its memory allocation is different because remember, if we're just putting our values from our list into a new heap, that list still exists in memory. And now we have created a new heap as well, right? And so both of these are storing the exact same information. And so the memory allocation we say has theta n. In-place heap sort is a lot better. Unfortunately, we don't have time to go into it in this mini lecture, so definitely go into your textbook and check out how exactly it is done. But essentially what we're doing is we're creating a heap by manipulating the values in the list itself. And so we're not creating a new heap, we're just changing the ordering of stuff in our list. And well, because we're not creating a new data structure that has a memory allocation of theta 1, and therefore it is much better for us. Heap sort is really great. Sorting items into a heap takes O n log n runtime, which is significantly better than n squared runtime. However, it is a bit strange because heap sort doesn't give us a list, right? It gives us a heap. And as you can see, removing the largest item from a heap is going to take O log n runtime, whereas removing an item from a list, for example, takes much less time. It's like constant runtime, right? And heaps are also a bit strange because you can't access the indexes of a heap like you could in a list. And so it is not always preferred for us to use heaps. Now let's look at merge sort. The basic idea behind merge sort is we're going to break a list into halves. Then we'll connect the merge sort on both of those halves, and we're going to merge the 2 sorted lists together in a process I will soon describe, right? So as this is a recursive function, so let's think about, let's take a look at how this is done, right? So we start in this array with this list 10, 8, 0, 7. We're going to split them in half to get 10, 8, and 0, 7. Then we're going to merge sort these. And we're not going to really think about how it is done yet, but just know that we're getting 2 sorted arrays from this. So now the question is, how can we merge 2 sorted arrays together? Well, this kind of gives a clue as to the process, right? What is essentially happening is once we start with like an output list that is of n size, that is quote unquote empty, right? And we're going to put values into this. And when we put a value into our list, we're going to mark it as used, right? And so how do we do this? we're going to take the leftmost non-used value from each of the two sorted lists and compare them. Whichever of them is smaller, we're going to put it into the output array and it is marked as used, right? So let's go step by step. Well, first of all, we're going to compare 8 and 0, right? 0 is smaller than 8. So we're going to put 0 into the output. As you can see here, this line is drawn here. And once we put 0 into the output, it is marked as used. So now when we compare the two leftmost unused markers again, it's going to compare 8 and 7. We're not no longer going to compare 0 because 0 has been used. Well, now 7 is less than 8. So we're going to put 7 into here and mark 7 as used, right? And so all the values in here are used. And so therefore, we're comparing 8 to essentially nothing, right? And so now we're going to put 8 here, mark 8 as used. Then we're going to look at 10, compare 10 to nothing, and then put 10 into here and mark 10 as used. And that is done, right? So how long does this process run for, right? Well, essentially, we're running the comparison n times because eventually we're going to put n values into the output array. And so therefore, this is going to take theta n runtime. Okay. All right. Well, if this singular process takes theta n runtime, then how long does merge sort take overall? Well, the first, as you can see here, this took theta n, right? But before we were able to do this process that took theta n, we needed to sort this 10-8 array and the 0-7 array, right? And how long did those take? Well, it is corresponding to the length, right? And so therefore these two have length of n over 2. And so we had to do n over 2 on each of these. But wait, before we sort 10 and 8 and 0 and 7, we need to divide those in half as well and then sort each of those. How long are those? Well, they all have length of n over 4 and therefore have runtime n over 4 to conduct merge sort on those. And so as you can see, we're starting to form a pattern that you might be familiar with from asymptotics. If you look at this pyramid, and imagine this pyramid goes down forever, the sum of the values on each row of this pyramid is equal to n, right? So we have n, and then we have 2n over 2 and 4n over 4. And so therefore each row is going to take n runtime. And then we have to consider how many rows are in this pyramid. Well, we go from n to n over 2 to n over 4 to n over 8, etc. Well, pretty clearly it's going to have log n height, right? And so therefore in total we have log n times n runtime to create our merge sort. Merge sort is really great. Just like a heap sort, it is faster than selection sort. And in addition to that, it also gives us a nice list, which is generally easier to use than a heap. But now let's consider one last sort called insertion sort, which has unique cases in which we would prefer to use insertion sort. It's a bit complicated to describe, but essentially we're adding each item from the input into the output. Then we're going to quote unquote insert into the output in the right place. Insertion sort also tends to be the fastest on small n, for example, less than 15. You don't have to understand the theory behind this at all. This is very complicated and it's not out of the scope for your class. But empirically speaking, we've started to notice that insertion sort is really, really fast compared to all the other ones on really small n's. And so basically what this is saying is that if you see in a test that says, oh, which sort should we be using? And it gives us specifically that our n is small, then insertion sort is going to be the correct answer. That's all you have to know. All right, so what exactly is the process of insertion sort? Well, let's go step by step. On this example, I pulled from your slides. We want to sort the word potato in alphabetical order. So we're going to start on the left-hand side and move our way right. And at each step, we're going to insert our current value into whichever space it needs to be at, right? So first of all, we're going to insert P into our output, and there's nothing in the nothing else in the output, so it is currently alphabetical order. Then we're going to insert O into our output. We're going to consider P and O. Well, O comes before P in alphabet, right? LMNOP, right? In that case, we're going to swap the positions of O and P, right? And so now O and P are in alphabetical order, and so therefore we can continue on. Then we're going to put in T into OPT. T, we're going to compare it to P, and T comes after the alphabet, so there's no issue there. All right, now let's try to put A in. OPTA, right? First of all, we're going to compare A to T and realize that we need to swap. Then we're going to compare A to P and then we're going to swap again. Then A to O and we're going to swap one more time. And now A is at the beginning. There's nothing else to swap with. And so we know that we are now once again in alphabetical order. And so we stop. That takes 3 stops total. Next, we put T in again. T compares to T and realize there's no need to swap. And then finally, we put in O. O compares to T. It swaps. O compares to T again. It swaps. O compares to P. It swaps. O compares to O, there's no need for swapping, and so therefore this function concludes, right? And so how long does this take? Well, there's actually a best case and a worst case scenario in this particular example, right? In the best case scenario, our function, whatever input we put into is already in a sorted list. And so in that case, all we have to do is move, all we have to do is iterate through the thing, and there are no stops necessary, and that takes omega n time, right? There's going to be a slight error on the sides where I write omega 1. It should be omega n because you have to iterate through every value in the word, right? However, what is the worst case scenario? Well, imagine a worst case scenario in which whatever word we're sorting alphabetically or whatever numbers are sorted alphabetically by size is in the reverse order that we want it to be. Well, in that case, the first thing that we're going to put in is going to have to be swapped once. Then the next thing we're going to put in is going to be swapped twice. Then it's going to swap 3 times. Then so on and so forth until it gets swapped n times, right? And so if you realize that is exactly how selection sort works. And so therefore, that sum is 1, 2, 3, n is going to be equal to an n squared type. And so it's omega n o n squared. All right. And the most common, there are going to be questions on the test, which are going to test you on the implementation of different sorts. And so therefore you should understand what the process is exactly. And there are going to be questions on the test that will test you on which sort is the most useful in a particular instance. And so it's really good to understand what the runtimes of each of these are. Selection sort is basically worthless. It has theta n squared for both best case and worst case, which is terrible and worse than every other one. So that's almost never the right answer. Heap sort has a worst case of n log n and has a best case of n because of the way that inserting into a heap works. However, heap sort also has its own limitations, which have to do with the fact that it's returning as a heap. Removal from a heap is more complicated. Accessing items in a heap that aren't exactly the largest is going to be more complicated. And so, generally speaking, we also don't use heap sort when we can use one of the other sorts. Merge sort and insertion sort are the two candidates that you learned about currently that are going to be most likely to be used. Merge sort is kind of the all-arounder. As you can see, it always takes n log n and best case and worst case. But insertion sort is slightly different because it has a best case of theta n, which is faster than merge sort, and a worst case of theta n squared, which is slower than merge sort. And what that means is that if we're given a scenario in which insertion sort is almost in its best case, then insertion sort is going to be better than merge sort. So an example in one of the questions I saw in your textbook was if we took a sorted list and then we just changed one of the values in the sorted list, so it is no longer sorted, would merge sort, insertion sort, heap sort, or selection sort be best? Well, in that case, we are almost already in the best case scenario of insertion sort, which is where everything is in a sorted value. And so therefore insertion sort is better in that case. One small last important note is that insertion sort, remember, is better for very small values. So once again, always make sure to keep that in mind as a note. But aside from that, that is it for our sort review. Thank you very much for watching.